Welcome to yet another practical example. To make sure you understand how all of these new terms are applied in practice, we are going to go over some real-world data. In particular, we will examine student population statistics for Hamilton College during the 2017-18 academic year. We will apply Bayes' law to determine whether the college is successfully diversifying its student population. Since the college only provides a 4-year program, any representation higher than 25% would indicate a higher than average value. Okay. To conduct our analysis, we are going to examine the common data set for Hamilton College for the 2017-18 academic year. The Common Data Set, or CDS for short, is a free public data set of summarized statistics about the demographic of the students attending a given college. A new dataset is released after the start of every new academic year. Furthermore, these sets are available for public use and can be found either through the College Board website or the site of the specific college you're interested in. In this instance, we visited Hamilton College's official webpage and typed in CDS into the search bar. Out of the results of our search, we chose the one for the 2017-18 academic year. Great! Now that you understand the data, we can start off by opening the CDS 2017-2018 PDF file attached to this lecture. As you can see, Section A is titled General Information and includes basic information about the college, like contact details and whether it is coeducational or not. This information is important in general, but it is not relevant to our goal, so we skip it and jump to Section B on the third page. This section is titled Enrollment and Persistence, and it showcases enrollment in the college divided into different categories. Now, that's something we'll make use of. Let's start off by examining Table B1, which showcases the distribution of students based on their gender. Since the survey students fill out to apply only has the options male and female, the data is split solely into these two groups. Now let's spend some time ensuring you interpret the table correctly, because we will be examining similar ones throughout the lecture. Start off by examining the 4 different columns in the table. They represent full-time and part-time students separated by gender. More precisely, the first column showcases full-time male students, and the second one showcases full-time female students. The third and fourth column represent part-time male and part-time female students accordingly. Now let us look at the rows. We see that they are split into 2 major groups as well: undergraduates and graduates. Since Hamilton is a liberal arts college, it is an institution which only offers bachelor's degrees. There are not graduate students. This explains why no numeric values feature in the lower half of the table. Furthermore, all claims we make will be about undergraduate students. Therefore, the number 217 in the table is part of the first column and the first row. Therefore, the people included are simultaneously full-time males and degree-seeking first-time freshmen. In a Bayesian sense, these 217 students represent the intersection of the sets denoted in the first row and the first column. Let's observe the total undergraduates row. It includes all degree-seeking and all other students enrolled in credit courses. This means that the value 1,000 we observe in the 6th row of the second column is the union of all full-time undergraduate women in the college. Since there are no graduate students, 1,000 is actually the union of all the full-time women in the entire college. Now, the union of all women, both full-time and part-time, would be 1,000 plus 9, or 1,009. This is true because no students can be simultaneously part-time and full-time. A Bayesian way of expressing this relationship would be to say that the sets of part-time and full-time students are mutually exclusive. Additionally, we have 886 plus 2, or 888 male students attending the college. Below the table, we are provided with the total number of enrolled students, which is 1,897. Since there are 1,009 women and 888 men, they combine to complete the sample space. Furthermore, due to the nature of the survey, nobody was allowed to mark any answer different from male or female, so the two sets have no overlapping elements. Satisfying both conditions means the two sets are complements. All right, Now that you are well acquainted with how to read these tables, we will move on to a different part of Section B. Namely, we will focus on the racial ethnic diversity in the college summarized in Table B2 below. We want to use Bayes' law to determine whether the student body is successfully diversifying its population. Therefore, we need to use the table to determine whether the freshman class is more diverse than the average for the specific ethnicity. To do so, we need to be able to accurately compute the appropriate size of each set we are interested in. Let event A be for a degree-seeking first-time first-year student, and event B being Black or African American non-Hispanic. For convenience, we're going to refer to elements of A simply as first years and elements of B as Black. Since we have a total of 1,897 students and 480 of them are first years, then the probability of being a freshman equals 480 over 1,897, or 0.253. This suggests that approximately 25.3% of the student body are freshmen. Similarly, we can estimate the probability of a random student at the institution being of African American descent. That would equal 80 over 1,897, or 0.042, or close to 4.2%. Now, the intersection of A and B would represent all Black first-year students. Going back to the table, only 26 students represent both demographics. The probability of being a Black first-year student is 26 over 1,897, or 0.014, which is close to 1.4%. We know the likelihood of a student being African American, and we know the chance of a random student being both Black and a freshman. Thus, we can use the conditional probability to see that the likelihood of a Black student being in his first year at the college is 26 over 80, or 0.325. This value is significantly greater than the expected average of 0.25, so we can see a rising trend in the representation of minority in the student population. The union of A and B represents all students who are either first-time first years or Black. We know that there are 480 first years, 80 Black, and 26 first-year Black students. To find the number of students within the union of A and B, we would apply the additive law. According to the additive rule, we would have 480 plus 80 minus 26, or 534 students that are either freshmen or Black. Once again, we would find the probability of being part of the union by dividing the size of the union by the size of the sample space. In this instance, that would be 534 over 1,897, or 0.281, which indicates that approximately 28.1% of the student body is either a freshman or identifies as Black. So far, so good. Now, suppose C represents the set of all Hispanic Latino students at the college. Since event B clearly says non-Hispanic, then the two must be mutually exclusive. Thus, the intersection of the two is the empty set, but their union equals the sum of their elements. Therefore, according to the table, there must be 167 plus 80, or 247 students who identify as either African American or Latino. The probability of picking a random student and them identifying as either one equals 247 over 1,897, or 0.13, which equals 13%. Not that great as a percentage, but great work on figuring that out. You could surely find out these and other relationships on your own. However, let's dig a bit deeper and examine some conditional probabilities. In Table B2, the entire first column only represents values for first-year students. Therefore, any number we get would represent the size of the intersection of freshmen and another demographic. This is important when we wish to compute conditional probabilities. Recall that the conditional probability formula states that the likelihood of an event occurring, given another event has already occurred, equals the likelihood of the intersection over the likelihood of the second event. A more precise example would be the following. The likelihood of being Black, given you are a freshman, equals the probability of being a Black freshman over the likelihood of being a freshman. We can simplify this to the size of the intersection over the size of the second set. In our example, that would mean 26 over 480, or 0.054. Therefore, there is a roughly 5.4% chance for any freshman student to identify as Black. Similarly, we can compute the likelihood of a given student to be Hispanic first year. We can compute the likelihood of being a Latino, given you are in your first year of college, as well as the likelihood of being a freshman, and apply the multiplication rule. Let's begin. We start by examining events A and C, being a first year and being Latino. The likelihood of being Latino, given you are a first year, equals the number of Latino students who are first years over all first years. According to the table, that equals 57 over 480, or 0.119, which is close to 12%. So far, so good. Now that we've computed both probabilities, we can plug the values into the multiplication rule. The probability of being a freshman is 0.253, and the probability of being Latino, assuming you are a first year, is 0.119. By multiplying the two, we get 0.03, or a 3% likelihood of being a Latino first year. Great job! What if we want to find out the likelihood of being a freshman, given you are Hispanic? We could calculate this using two different ways. In the first one, we would simply apply the conditional probability formula like we did earlier. However, we could also apply Bayes' law to solve this. According to the theorem, the likelihood of being a freshman, assuming you are Hispanic, equals the likelihood of being Latino, given you are a first year, times the probability of being a freshman over the probability of being Hispanic. Next, we estimate the likelihood of being Latino, which is 167 over 1,897, or 0.089, and that is close to 9%. We have estimated all three of the required probabilities, and they are respectively equal to 0.119, 0.253, and 0.089. Plugging these values into the formula gives us 0.199 times 0.253 divided by 0.089, or 0.338. That means there is a 33% chance a student is a first year, assuming they are Hispanic. Thus, we can say that a person is more likely to be a first year, given they are Hispanic, than to be Hispanic, given they are a freshman. If we think about the favored overall formula, this makes sense because there are more freshmen than Hispanic students in the college. Such a characteristic is fairly common among small liberal arts colleges in upstate New York, so the insight does not surprise us. Phenomenal work! We examined several tables from the Common Data Set for Hamilton College for the 2017-18 academic year, and our short analysis suggests that the college is improving its minority representation with the current freshman class. However, further research would be required to account for attrition among the student population, as well as moving to other colleges within the region. Even though our analysis may not have been full or conclusive, we made full use of our understanding of Bayesian notation to reach some insight about the data. This shows how important Bayesian inference is in terms of analytics and how understanding the relationship between sets and events can help us reach important conclusions. For homework, you can explore Section C of the CDS, which summarizes first-time, first-year admissions. Compute what the likelihood of a first-time male student to be accepted based on gender and determine whether being male or female had any effect on your chances of acceptance. Furthermore, determine whether first-time freshman women were more likely to enroll than first-time freshman men. To find both of these, you need to examine only the tables in Part C1 of the CDS. Additionally, you can practice your understanding of probabilities by exploring the values in Table C2 and determining the likelihood of being offered a place on the wait list. Additionally, you can compute the chance of being admitted, having accepted a place on the wait list, and the likelihood of getting admitted given you were offered a place on the wait list. In the next section, we're going to start talking about probability distributions, how to properly apply them, and why understanding the most commonly featured ones is so important. Thanks for watching.